A telescope camera snaps another routine image of the sky. Nothing dramatic, just stars, a faint smear, a number in a database. But over the next few weeks, that smear refuses to stay the same. Its color shifts, its glow changes, and its chemical fingerprints hint at a history stranger than a normal comet. Then the orbit solution lands, and the meaning of the discovery sharpens. This object did not form here. It came from another star system, crossed into ours at high speed, and now it is changing in ways we did not predict. If we listen carefully, it might tell us something about worlds we cannot visit. Tonight, we follow the clues, and we keep feet on evidence. Picture this. Something slips into our solar system from the deep dark between stars, and at first it looks like a faint smudge, easy to miss. Then it starts acting wrong. Its glow changes from red to green to gold. Its surrounding cloud releases chemicals that do not line up neatly with the comets we know, and its path through the sun's domain tells us it was never truly ours. This object is called 3I Atlas, and it is only the third confirmed visitor we have seen that came from another star system. That alone would be headline-worthy. But what makes 3I Atlas strange is not just where it came from, it is what it does once it gets here. In astronomy, color is not decoration. Color is physics. It is temperature, chemistry, and sunlight interacting with dust and gas. When an object changes color, it is telling us its surface and its coma are evolving in real time. So the obvious question becomes hard to ignore. What kind of interstellar body changes its appearance this dramatically in a matter of months while crossing our skies? Over the next few minutes, we are going to follow the evidence, like detectives with telescopes. We will trace how 3I Atlas was found, what the measurements actually show, and why even careful researchers have been forced to use words like unusual, unexpected, and puzzling. Some ideas will be ordinary, some will be weird. All of them will be tested against what we can observe. Because with 3I Atlas, every strange detail might be a clue, and we do not get many clues from other stars. And if we do this right, we will end not with a neat answer, but with sharper questions and a better sense of what to watch next. The story begins in July 2025, when sky surveys were doing what they always do, taking repeated images of the same star fields, night after night, hunting for anything that moves. Most moving points are familiar. Asteroids bound to the sun, comets with predictable behavior, space rocks with paperwork in our databases. But one faint object stood out because its motion did not match the usual patterns. It was flagged, logged, and shared, the way modern astronomy turns a suspicious pixel into a story. In many cases, the first alert comes from automated pipelines linked to projects like Atlas, Pan-STARRS, and other wide-field searches. Software compares images, rejects noise, and highlights candidates for humans to confirm. That confirmation step matters, because a fast mover can be a near-Earth asteroid, a satellite artifact, or a data glitch. With 3I Atlas, repeated detections held together. Once the orbit was refined, scientists also estimated its inbound speed relative to the Sunday interstellar objects arrive moving quickly because they are not falling from rest within the solar system. That high approach speed, paired with the open trajectory, is the signature that told everyone this came from far away. Follow-up observations came fast. Astronomers measured how its position shifted against background stars and fed those measurements into orbit calculations. Very quickly, the math pointed to something rare. The object's trajectory was not a closed ellipse like a typical comet. It was a hyperbolic path, an open curve that comes in once and leaves forever. In plain language, it was not orbiting the Sunday, it was passing through. At that point, the discovery became bigger than a new comet. It became a new interstellar object, the third one ever confirmed. The first one, Oumuamua, looked oddly asteroid-like. The second, 2I Borisov, behaved more like a familiar comet. 3I Atlas landed in a more uncomfortable zone. It showed strong activity early, yet carried signatures that did not look like a simple copy of Borisov. To tighten the measurements, teams used a mix of instruments. Optical telescopes tracked its brightness and shape. Radio facilities and networks that can support deep space tracking, including systems like the Green Bank Telescope and the Deep Space Network, were discussed as part of the broader effort to constrain motion, search for emissions, and coordinate timing. The goal was not drama, it was precision. Then came the first hints of trouble. The speed and direction were consistent with an interstellar origin, but the way its surrounding coma brightened and evolved seemed out of step with expectations at its distance from the Sunday. Researchers were careful with language, but the implication was clear. This was not just a third visitor, it was a visitor with quirks. By the end of the initial discovery phase, 3i Atlas had done its most important trick. It turned a single detection into a list of questions and forced the community to watch closely because the next data points could change the story. Once the headlines faded, the real work began, turning a moving dot into a physical object with measurable properties. Astronomers started by collecting light in as many ways as possible. Ordinary images in visible light show brightness, shape, and how the coma spreads. Infrared data hints at warmer dust and larger grains. Ultraviolet can reveal certain gases. And spectroscopy, the workhorse of comet science, splits the light into a barcode of chemical fingerprints. Here's the expectation. If 3i Atlas were a fairly typical comet, sunlight would warm its surface, ices would sublimate, and the escaping gas would drag dust outward, building a coma and sometimes a tail. The spectrum would show familiar species like water-related fragments, carbon compounds, and cyanogen. The brightness would change smoothly as distance to the sun changed. None of this would be shocking. But the measurements, as reported by observers and summarized in public discussions, did not stay in the comfortable lane. Early on, 3i Atlas appeared unusually active for its distance, as if only a thin crust separated volatile material from space. That matters, because an object that wakes up early is telling us something about its surface layering and thermal history. Then there were the chemical surprises. Spectra described strong dust with organic, rich character, consistent with very dark, reddish material. Later, a shift toward greener emission suggested a different mix of gas in the coma, the kind of change you would expect when new volatiles start dominating what is escaping. And after that, observers began describing a move toward a more golden, dust-dominated color, as if the gas-rich phase had peaked and declined. One particularly intriguing thread involved metal emissions. Reports discussed a rise in nickel signatures without a matching rise in iron. That does not mean the nucleus has no iron. Spectra mostly probed the coma, not the interior. It means that whatever was escaping into the coma favored nickel-bearing molecules, while iron either stayed locked in solids or reacted before it could be observed. Chemists have suggested candidate pathways involving metal carbonyl compounds because some of those can form at low temperatures and break apart under solar radiation, releasing metal atoms into the coma. Distance also matters, and not in a vague way. Around 2.5 astronomical units, there is a practical threshold where water ice can become much more active because solar heating reaches a regime where sublimation accelerates. If an object's behavior changes near that region, it can signal a transition from carbon monoxide or carbon dioxide-driven activity toward water-driven activity. That shift can rewire the coma chemistry and even change how dust is lifted. Put all of that together and the scientific puzzle becomes clear. 3i Atlas looks like an interstellar object, moves like one, and yet it behaves like a moving chemistry experiment. Its light, its color, and its emissions keep evolving. The hardest part is classification. Is it a comet that just happens to be exotic, shaped by a harsh past around another star, or are we seeing a process we have barely sampled before? Whatever the answer, the object tells a story through light, and we learn to read it. A useful scientific habit here is to separate anomaly from explanation. The anomaly is real, the changing colors, the evolving emissions, the early activity. The explanation is still under construction. And that is why the data section ends with a question that refuses to go away. Are we watching a strange comet from another star, or a category of interstellar object we have not learned to name yet? By this point in the story, the mind wants to finish the puzzle. It sees strange behavior and reaches for an explanation that feels complete. Science does something more disciplined. It builds multiple hypotheses, then asks what each one would predict and whether the data fits. Start with a natural theory, because nature is extremely good at producing weird things without asking for our permission. In this view, 3I Atlas is a comet-like body from another star system, but one with an unusual past. Imagine it spent a long time as a short-period comet around its original star, looping close again and again. Each pass would bake off the most fragile ices and leave behind a tougher crust, rich in organics and darker compounds. Then, through a gravitational encounter, it was ejected from its system. That interstellar journey can last millions of years. In that time, the object is in deep freeze, but it is not in perfect isolation. It passes through thin clouds of gas and dust and is constantly hit by cosmic rays. A thin surface layer can be chemically altered, and it can accumulate volatiles in small amounts. When 3I Atlas finally entered our solar system, sunlight could have triggered a rapid awakening, first releasing the easier-to-mobilize compounds, then shifting as new layers were exposed. That sequence can produce changing colors, changing gas species, and phases where dust dominates. The nickel puzzle also fits within natural chemistry. If certain nickel-bearing molecules volatilize more readily or survive transport into the coma more easily than iron-bearing ones, you can get a skewed spectral signature without any exotic origin. In other words, the object may be normal in bulk, but selective in what it releases. Now, the artificial theory. This is the one that tends to show up whenever an interstellar object behaves oddly, because our sample size is tiny and our imaginations are large. The idea is simple to state. What if 3I Atlas is not just a natural body, but an artifact, a probe, or a piece of technology passing through? A scientific way to treat that idea is not to mock it and not to worship it, but to ask what evidence would be required. An artificial object might show non-gravitational acceleration that cannot be explained by outgassing. It might show coherent radio emissions with patterns inconsistent with natural sources. It might maintain a geometry, rotation, or brightness change that does not match dust and gas physics. So far, none of the publicly discussed observations force us into that corner. There is also a deeper reason for caution. When you do not fully understand an unfamiliar natural process, it is easy to mistake complexity for intention. Comets fragment. Their activity turns on and off. Their colors shift with chemistry and sunlight. A rare interstellar comet can easily look like a rule breaker simply because it was made under different conditions than the comets we grew up studying. Most importantly, interstellar objects carry the chemical history of their birthplace, so the strange parts may be simply our unfamiliarity, not the object. So where does that leave us? Both frameworks, natural and artificial, can be spoken aloud. Only one is currently supported by the way the evidence behaves. Yet, even the natural story is not complete, because 3I Atlas keeps changing faster than our confidence can keep up, and that is the honest place to end this section. Not with a verdict, but with a disciplined mystery waiting for the next data point. All of this brings us to the next major checkpoint, the close encounter with Jupiter expected in March 2026. Jupiter is not just a pretty planet with stripes, it is a gravitational laboratory. When a small body passes near it, Jupiter's pull can bend the trajectory, change the viewing geometry, and sometimes even stress the object enough to reveal weaknesses. For scientists, the flyby is valuable for two reasons. First, dynamics. If we can measure 3I Atlas's path with high precision before and after the encounter, we can test whether its motion follows pure gravity or shows extra accelerations. Small deviations can point to subtle outgassing jets, fragmentation, or changes in mass distribution. Second, physics. As the environment changes, the coma may evolve again. A weakening object might shed dust. A stable object might simply fade as it loses volatiles. There is also a practical detail that matters for interpretation. Jupiter's gravity will change how we see the object against the star background, and that affects photometry, the measurement of brightness. Teams will combine ground-based telescopes with space-based assets when possible because different wavelengths can help separate dust from gas. Amateur observers can matter too. A global crowd, taking repeated images night after night, can catch short-lived outbursts or a sudden split of the nucleus, events that a single schedule might miss, and help confirm trends across the sky. There is a quiet tension here. If the object behaves exactly as expected, that is still a win. It strengthens the natural explanation and helps constrain models of its composition. But if the path deviates in a way that cannot be explained by normal cometary activity, the mystery deepens and the burden of proof shifts toward new mechanisms. Observers will be watching for changes in brightness, sudden outbursts, tail structure, and any sign of fragmentation. They will also watch the color. If the gold hue is truly dust-dominated, it may persist, or it may shift again if fresh gas-rich material becomes exposed. The challenge is that 3-eye atlas will likely become harder to observe as time passes. Interstellar visitors do not stick around, and the best data often comes from a narrow window. March 2026 is one of those windows. It could be the moment when this object either settles into a familiar story or writes a new chapter we did not know how to read. So where are we now? An object from another star system entered our solar system, and instead of behaving like a quiet, predictable comet, it kept changing. First it looked deeply red, then it shifted toward greener emission, and now observers describe a more golden, dust-driven glow. Along the way, its spectra raised eyebrows, including reports of unusual metal signatures and chemistry that does not fit neatly into a familiar category. We followed the trail from discovery to data. We saw how orbit calculations tell us it is interstellar, meaning it is not bound to the sun and will not return. We looked at how researchers use imaging and spectroscopy to infer what is in the coma and why the coma is not the same thing as the nucleus. We explored the best natural explanations, including a history of heavy heating around its home star and later accumulation of material during its long interstellar cruise. And we allowed one more idea into the room, the artificial hypothesis, not as a conclusion but as a test of standards. What evidence would we need before we accept something extraordinary? So far, the answer is more than we have. The next chapter arrives with Jupiter in March 2026. The flyby will test its motion, its stability, and its evolving chemistry. Maybe it will fade into the background as a strange but natural comet. Maybe it will surprise us again. Either way, 3-eye atlas leaves us with a question that feels bigger than one object. If 3 interstellar visitors have already crossed our path in a short span of years, how many more pass unseen, and what stories are they carrying, written in light, from places we have not yet learned to name? We should keep watching, because the universe rarely repeats itself.